Hello and good afternoon.
Hello, what's going on?
No, not much. Excited about today's class because hopefully finally stuff will come together. I think we've been doing a lot of this physics stuff, and I don't know if anybody sees where it's going or why we're doing some of it. So hopefully today that will work out.
Yeah.
Hi, Dr. Farusa.
Good morning, Dr. Panasi. Good morning, everyone. Good to see you.
Glad
Good
you
morning.
could join. I noticed, Caldrian, you didn't get a chance to come last class. Is that correct?
Yes, sir. I had to report to the base, of course, for my job on Wednesday.
Were you able to watch the video?
Yes, sir.
Okay, good. Good. It always helps when everybody's up to speed.
Yep.
Because we always build up on the last class. So I always say,
Yeah.
make sure to watch the last class before we go into the next one.
Yes.
Cool. Well, I'll wait just a minute for folks to get here and then we'll get started. Yeah, all this physics stuff will hopefully start to make sense why we're calculating it. If the idea is that the Earth is warming and the sun's heating the Earth, it's really important to understand black body radiation because that's what happens to all that energy, right? It heats up the planet and then the planet radiates out, this energy. And as we've seen, from the spectra in our last couple classes, is at the temperatures that we're at and that these bodies are reaching, we're emitting mostly in the infrared. And that's really, really important when it comes to climate change. So that's where it's going to tie in greenhouse gases and all that kind of stuff. And we may get to actually composition of the climate today, not 100% certain, but hopefully we'll get close.
Dr. Panasik, I wanted to find out, I may have missed this, but all the teachings you do, are those the ones that you are saying are posted on YouTube?
Yeah, so all of the lectures that I do, they're posted on our Moodle, but I know sometimes people have connectivity issues, and for a little while, some students couldn't get into Moodle. I don't want that to be a problem, so I've been posting them to YouTube. Now, I don't make them public because there are students in there. Maybe you don't want, folks seeing you, but if I send you the link, you should be able to click on it and see it. And I think I've sent out also the playlist. So if you just go to the climate change playlist, and I can I'll resend it out again today when I send out the link for this one. That should have all of them there, and you can just tool through the playlist.
All right. Okay. Thank you so much.
And I think everyone is there except for the first day. That one didn't get recorded.
All right. All right.
Okay.
Yes.
Well,
thank you.
Okay, great. So now we got folks filtering in. Hi, Mungo. Now, I did get a chance to watch all of your Flipgrids. I'm in the process of uploading all of my responses, so I have those as well. Your grades have been entered onto Moodle. But watch for those responses because I try and kind of, add some details or explain some things extra. Y'all did a really good job. Don't get me wrong. I just like people to be, there with those numbers when it comes to climate change, because you're going to be using them over and over and over again. And so you should just, what are those indicators? How are they measured? What are anomalies? That kind of thing. I'm working on what the next flip will be. It'll probably be about how to do these climate change models. So pay attention. Okay, I'm going to go ahead and get started. Hey, Shepard, glad you're here. Let me go ahead and pull up this wonderful PowerPoint. And that's not what PowerPoint looks like. There we go. So we're going to start talking about climate modeling. What we've talked about so far in the last week is some of the physics that we're going to need to understand to do climate models and just how global warming works. We talked about what power is. It's energy per second. We talked about energy that's usually measured in joules. And we had to talk about power because we have to talk about how energy moves from one place to another, right? And so how it moves from the sun to the earth is really where we're going with it. And one of the examples, I'm going to stop the share because I'd like you to be able to see me. One of the examples that we talked about is if you have any object, whether it's this cup or any object, you're going to find that if it's sitting in a room, all this energy's coming up, it's going to come up to room temperature, and that object acts as a black body. So it's going to radiate energy out based on its temperature. And if it radiates out less energy than it takes in, it's going to start accumulating energy. And remember, internal energy is the same thing as temperature. Temperature is just the average kinetic energy of molecules. So it just means as they gain energy, they vibrate faster. And one of the things that we learned about when they're vibrating faster, we're talking about the molecules and atoms. Remember, atoms are surrounded by electrons, right? They have these electron clouds around them. Well, whenever you move a charged particle, you create a magnetic field. And so the more these things vibrate, they're creating this magnetic field. And when that drops down, it emits a photon. And so anything of any temperature above absolute zero is going to be vibrating. And if they have electrons and protons, they're going to be generating electromagnetic field, which means they're going to be emitting photons. And we learned Wien's displacement law. That's the one that allows you to tell what wavelength of photons are going to come out based on temperature. But that's just the peak wavelength, right? And so then we looked at the Stefan Boltzmann relationship, which tells us, well, you can actually tell the complete energy of the photon coming out, how much power this object is radiating. And Stefan Boltzmann gives you power per unit area. And so if you know the surface area of the object, then you can really tell how much power it's radiating. And, just like if you take a turkey out of the freezer, and you set it in a room temperature room, its temperature's lower. So the amount of power that it's radiating is lower, but now it's taking in power from the surrounding. All these infrared photons being emitted from the rest of the room are hitting the turkey, it's absorbing it, so its temperature increases because it's emitting less energy than it is taking in. And so eventually when it takes in enough energy, the amount of energy going out and the amount of energy coming in will be the same. And then it reaches homeostasis, it reaches balance. The temperature will stay the same. It won't change temperature. And so this is our overwhelming concept or overarching concept in climate change is that the energy in has to equal the energy out. That's called energy balance, and that's what determines our climate. If we get more energy in than we're letting energy out, then we're going to accumulate energy, and that means the temperature is going to rise. Okay. And we did a very, very simple climate calculation last time, is where we ended up with it. We assumed that the Earth was acting like a black body, and we know what the solar constant is. And so using the solar constant, we calculated just how much power is coming down onto the planet. And we use the surface area of the circle of the planet that the light is hitting to determine that the sun is giving us 238 watts per meter squared to every single square meter on the planet. And for the planet to stay the same temperature, energy in has to equal energy out. So that would mean that each square must also emit as black body radiation 238 watts per meter squared. And so we have this relationship, the Stefan Boltzmann relationship, which you can rearrange to figure out, if you know the power that a black body is radiating, what's the temperature? And that's defined by this little formula here. It's the fourth root over the power divided by the Stefan Boltzmann constant. And when you calculate that out, it gives you a temperature of 255. Well, 255 is actually not the average temperature of our planet. So what's up here? You know, we're 33 degrees Kelvin below the actual surface temperature when we make this calculation. And all we've done is we've taken the power of the sun hitting the planet and then saying, well, eventually the planet will have to heat up enough that it's radiating the same amount of power back out into space. And so it's not accumulating energy anymore. It's not losing energy. So it will stay the same temperature. So this tells us what our equilibrium temperature should be. But it's not. Can anybody explain why that's the case? I mean, we've calculated how much energy is hitting the Earth. It warms up until it's going to emit the same amount of energy. And for it to do that, it would just only be, the planet would only be at 255 K. It's like minus 20 degrees Celsius. So what's wrong here? Why isn't this working? Anybody have any thoughts?
Where you is it indicating my first thought was it's kind of indicating that the Earth is not cooling since the temperature between since the calculated temperature isn't consistent with the temperature in Kelvin that's being radiating the Earth via the sun. So I'm assuming um, this would be a trend in which will be showing that the Earth is cooling rather than warming.
Right. This
Right,
would say
because
the Earth should be cooler, right? Because that's the temperature that it would radiate. So what's going on here? Now, remember, in this assumption, we're thinking about the Earth as just this static object, you know, like a basketball floating in space with, you know, the radius of the surface of Earth, right? What we're not taking into account is any kind of an atmosphere. Okay. And so I want to go through what happens with an atmosphere. And that's probably going to affect, because there's a lot of floating boulders out in space. And this calculation would be perfect if you're talking about an asteroid or a meteor. That's exactly where you would go with this calculation, and it would tell you the temperature of that object based on its distance from the sun. Now, remember, we used the solar constant S for being at the distance from the sun that the Earth is. So you might have to use a different solar constant if you're talking about a different planet because it's a different distance from the sun. But that's just for a rock. Now we have an atmosphere, and so there's a couple assumptions we're going to make about what's true about the atmosphere. So the atmosphere is transparent to visible photons. Okay, that's really important. And when we looked at the emission spectrum for a black body that's around between 5,000 and 6,000 degrees Celsius or Kelvin, and we looked at that emission spectrum, used Wien's displacement law, we can see that the peak wavelengths are well into the visible photons. That's why the sun gives visible light. It's also why we see in the range that we do, because if we saw in a range where the atmosphere didn't let the light that we were going to use pass, then we'd be like in a cloud and we couldn't see anything. So our atmosphere is transparent to visible photons, but our atmosphere absorbs infrared photons. That's going to be an assumption we're going to make, and we'll talk about why that's the case. So visible ones can go through freely. Infrared ones can't, but the sun is mostly emitting these visible photons. Okay. But if the atmosphere absorbs infrared photons, that must mean that it also acts as a black body and emits photons based on temperature. And since it's a black body, it's not just going to emit photons in one direction, it's going to emit photons in all directions, right? So it's going to emit photons equally up as well as down. Okay, and these are our assumptions that we've got for our atmosphere. And that's all we need to start this climate model. So let's start out. Whenever you do these climate models, you want to do a little drawing. I do this on the board, but instead I've just have them on here so you follow along. So you start by drawing the sun, then draw the surface of the planet, and then you want to put in an atmosphere. And I'm just going to draw it in as a layer, okay? Just as a layer, we're going to say we've got this layer of atmosphere. So this model is going to be what we call a one-layer atmosphere. Granted, things are more diffuse, but at least for the purposes of our calculations right now, we're just going to say we have a layer of atmosphere. So the first thing we want to do in our models is we want to draw the fluxes. Where is all the energy going to? So our first flux is the sun is shining down on the earth, right? And so we draw a line going from the sun to the earth. This is energy coming from the sun to the earth. And now we've said that visible photons aren't absorbed by the atmosphere. The atmosphere is transparent to those. So those photons pass right through the atmosphere as if it wasn't there and hit the surface of the earth. Well, what happens to that? Well, it heats up the surface of the earth. Surface of the earth gets warmer. As it gets warm, it's a black body. All physical objects made of molecules are black bodies. So their atoms are vibrating, and so they begin to emit photons. Well, the temperature of the sun was enough for its black body radiations to, those photons were in the visible spectrum. We know at the temperatures that we're dealing with on the Earth, use Wien's law, the peak wavelengths of the photons being emitted at those temperatures are infrared photons. So the infrared photons are now coming off the Earth. And remember, we put this layer of atmosphere here. So these photons are going to be absorbed by the atmosphere. That was one of our assumptions, is that the atmosphere can absorb infrared radiation. And so our third assumption then was that the atmosphere can act like a black body, which means if it's at any temperature above absolute zero, it's going to go ahead and do black body radiation and emit. Now, is it just going to emit out to space? No, it's going to emit equally in both directions. So for our atmosphere, as it heats up, it's going to emit photons both up and down. And so we draw our two fluxes. Okay. So now that we have all of our fluxes, we now have to start putting in some numbers, some energy. We know our solar constant at Earth's position away from the sun is 1,360 watts per meter squared. We have an albedo of 0.3. Remember, we went through those calculations prior. So we use this formula for energy into the planet is the solar constant times 1 minus the albedo divided by 4. When you plug those numbers in, the 1360 and the 0.3, that's going to give you energy in as 238 watts per meter squared. That's the same value we calculated last time. So that's the energy in coming here is 238 watts per meter. So we can put that number down here. Okay. Now, energy in has to equal energy out. So energy coming down from what we're calling our planet has to be equal to the energy going out from what we're calling our planet, going off into space. So which of these lines here, if energy in is coming 238, then energy out has to be 238. Which of these lines here is the energy out into space? I'll call this 1, 2, and 3. Yeah, 2. This is the energy out into space. So to follow our constraint of energy balance, energy in has to equal energy out. And so that means that that number is going to be 238. Well, if this number is 238, we said that if the atmosphere is acting like a black body, it's got to emit energy in both directions, right? It's not going to favor one direction or the other just because it wants to. So if we have 238 going out into space, then that means that we're going to have 238 going down as well. So this is what's hitting the planet from the atmosphere. 238 from the atmosphere and 238 from the sun. And again, we have this energy constraint, right? Where energy in has to equal energy out. So what's the energy into the surface? It's 238 plus another 238. And so that means that a total of 476 is going into the planet. So how much has to come out of the planet? So our sum of energy into the planet is 238 plus 238. So what is, yeah, so it's going to have to be the same amount going in, which is our 476.
So if there are multiple atmospheres, right, and it's a constant of 238, for example, if there are 3 atmospheres,
Yeah,
so would you would double, I guess you would double every time you go through an atmosphere with a constant of the sun being 238,
very
or
smart. We're going to work through that in just a minute. Let's just focus on the one layer atmosphere first, because we're almost at the end of what this tells us. So this is saying that the planet now, the energy out is 476 watts per meter squared, right? And so if a black body is emitting at this power, we can use that same formula. Remember, we have the Stefan Boltzmann relationship, which tells us that the power emitted is equal to the Stefan Boltzmann constant times temperature to the fourth. So we can use that crazy formula that we saw before, where we solve for T. We get T on one side, get the other points on the other side, which means you got the power here divided by the Stefan Boltzmann constant, and you take the cube, the fourth root of that. And so if we get back to there, that means with 476 as our power going in, if you solve for T, T is now equal to 303. Remember before, without an atmosphere, we had 255 is what the black body surface temperature would be. Now, when we put on one layer of an atmosphere, we get 303. A lot closer to the temperature that our Earth is actually at. And so what we see is that adding an atmosphere increases the temperature. So that's why our original calculation really didn't work, because we weren't factoring in that there's this layer of gas that's absorbing the infrared photons that should be streaming out into space. So we got energy coming in, but something is stopping all of the energy from leaving. It's getting absorbed into the atmosphere. And what does the atmosphere do? Well, it radiates, and it keeps radiating, but some of the radiation goes out into space, the rest comes back onto our planet, equal amounts. And it will keep heating up until the amount of energy going back out into space is equal to the amount of energy coming in from the sun. Our energy balance constraint. So is everybody getting how we're doing this, how we're getting this calculation? This is our first climate model. Any questions on this so far? Okay, I'm gonna go through it again, but now we're gonna try doing 2 layers because Caldrian's chomping at the bit. What happens if we got 3 or 4 layers? Because that's where we're going with climate change. So now we want to do a climate model with 2 layers. So we start by drawing the sun and the surface of the planet, but now we'll put in 2 layers of atmosphere. Okay, and so again, we're gonna draw our fluxes. We have a flux coming from the sun and it's going all the way. Why don't I stop at this atmosphere with this flux and heat this atmosphere up? Why is it going all the way down to the surface and not just to here? Can anybody tell me that? Why doesn't this line just go to the first atmosphere? I mean, the sun is hitting the atmosphere, the sun's light. Why doesn't it stop there? Hmm? What's our first assumption about the atmosphere? It's the atmosphere is transparent to visible photons. So if you're in the visible light range, it's as if the atmosphere isn't there. Those photons can go through freely. So this is just passing both layers of the atmosphere without getting absorbed, because the molecules that we happen to have in our atmosphere, other atmospheres of other planets can be different, but our atmosphere with the molecules that we have, for the most part, 99% of them don't, hold on a second, we're getting some noise coming from somewhere. Okay. Go right through the atmosphere. Okay. So that means we got energy coming from the planet, warming the surface. So our first flux is going to come from the surface, and then it's going to stop at this atmosphere, right? It's going to get these are infrared because we know the temperature. We're not as hot as the sun, so we don't produce visible photons. We're not at about 5,000 or 6,000 Kelvin. We're only closer in 300s. So all we're emitting is infrared. And we've already said that the atmosphere does absorb infrared. And so that means that when it gets to this first layer, this layer is going to heat up and it's going to act as a black body and emit energy. And it emits an equal amount of energy in both directions. So now we've got infrared going up and infrared going down. Now, this one can't go out to space because we've got a second layer of atmosphere here. So again, this is an infrared range. So this second layer of the atmosphere is going to absorb that energy and act like a black body. And it too will emit energy and in both directions. Okay. So it should look like that. We know from our solar constant, our energy in is equal to 238 watts per meter second. So of all these different, we'll call them 1, 2, 3, 4, 5, of all these different arrows, if we want to keep our energy balance constraint, which is energy in has to equal energy back out to space, which of these lines here should be 238? Because if we got 238 coming into the planet, we have to have 238 going out into space. Otherwise, it will continue to do that until the planet equalizes, until it satisfies that constraint. And we've been around here for 1 billion years, so this planet has satisfied that constraint. So which of these arrows should also be 238? 1, 2, 3, 4, or 5? Desire? Do you have this one here?
The first one in red.
Okay, so you're saying this one here? Okay, well, that's a problem. So if we're coming in at 238 here, this
Maybe.
arrow is not the arrow going out into space.
Yes.
Our energy constraint says the arrow going out into space has to be the
Yes.
same as this one here. So which is our arrow going out into space? 1, 2, 3, 4, or 5? It's in this upper atmosphere over here. This is what's going out into space. So energy coming into our system is 238. So the energy leaving our system has to also be 238. So this is the arrow that we're looking for. And this is gonna, these two numbers help. It's the outermost arrow, the one that goes out into space, that has to equal the energy in, because it can be a little bit I don't want to say confusing, but misleading, because you're seeing this arrow hit the ground, and so you think that the one that's leaving the ground should be equal to it. That's not our constraint. Our constraint is to the system. This arrow just happens to pass through the two atmospheres. But our whole system is energy in equals energy out. And so we're talking about the energy out. So the energy in from space equals the energy out to space. And that's this arrow up here. So if we know this arrow here, what other arrow do we automatically know? Caldrin, I think you're on mute.
You automatically know the one beside it, the third. Well, yeah, the third arrow.
Right. So this arrow here has to also be 238, because we know that this black body atmosphere emits the same in both directions. Okay. So we know 238 has to equal 238 coming in both directions. So remember, energy in has to equal energy out. So automatically we know another arrow. If we know these two numbers, we know this arrow. Why do we know this arrow? Because energy going into our black body has to equal energy coming out of the black body. How much energy is coming out of the black body? That is the second layer atmosphere.
238.
Well, it's 238 in this direction and 238 in this direction. So the energy coming out of this thing isn't 238. What is it? It's doing 238 up and 238 down.
So it's
Those are,
470.
yeah, it's 476. That's how much energy is coming out of this atmosphere. So how much energy must be going into that atmosphere? Energy in has to equal energy out. And so if all of the energy coming out of here is 476, then the amount of energy going in has to be 476 as well. Okay. If this number is 476, if this black body has to be radiating 476 in order for this atmosphere to be radiating out 238 into space and back again, then what is the value of this arrow here?
476.
Right? Because it has to equal the same up as it does down. So now with 476 going up, 476 has to also be radiated down. Now we can figure out this last arrow, right? What should the value of this last arrow be?
714.
Yep, very good. So how do you get that number? Well, energy in has to equal energy out, right? And so you're going to get 238 plus 476. Now, there's another way we could have figured this out, right? Let's see. And so when we take that, so there's another way we could have figured this out, right? Because we know that energy in has to equal energy out. And so we could look at this atmosphere and say, well, the energy out is 476 plus 476, but we're already getting some energy in. So we could add these two together and subtract that, and that will equal that. Or we could just add these two together because energy into the surface equals energy out, and this thing will still agree. And so now, if we know the how much the surface is radiating in black body radiation, we can use our Stefan Boltzmann equation, which gives us the power relationship of emitted to the temperature. And we can solve for T, and this is going to give us a temperature of 335. So adding another layer of atmosphere increases the temperature yet again, right? You can kind of see where we're going with this, because when we start talking about CO2, adding CO2 is like adding a layer. The more layers you add, the more the temperature is going to have to go up. The thicker, the more layers to this atmosphere, the more you're getting this greenhouse effect. So our conclusion is adding a layer of atmosphere increases the temperature. With no atmosphere, we got 255. With one layer of atmosphere, we got 303 Kelvin. With a two-layer atmosphere, we got 335. And in fact, there's a derivation in the book, and this is kind of where you were going with your question, Caldrian. Well, if you had 3 atmospheres or 4 atmospheres, so the equation that you come up with, the derivations in the book, is for an atmosphere with n layers, this is our equation for what the temperature would be, where it's just the number of layers plus 1. So remember, for a 1-layer atmosphere, we calculated there was for a planet with no atmosphere, our calculation was based on solar constant times 1 minus the albedo divided by 4 over the Stefan Boltzmann constant. We calculated that out to be 255. When we added an atmosphere, remember that was 238 coming in, but now it was like there were 2 of these 238s, right? And so then we got to 476. And then when we added another layer, this 714 came from adding another 238. So you can see with each layer that you add, it's just adding another one of those, because all this part works out to 238. And then we've got to take our 4th root of that. And so this will give us our temperature. Every layer is going to add on a little bit more. You know, like another 238, but then again, remember, you're taking the 4th root of that. So it's not going to be a linear increase. So we want to remember this calculation for an atmosphere with n layers. That's going to help us figure out what the temperature should be. And you want to remember our assumptions, which is the atmosphere is transparent, visible photons. The atmosphere absorbs all infrared photons. And then the atmosphere will behave like a black body and emit based on temperature, and it'll emit its photons equally up and down. So these were assumptions. Where do those assumptions come from? That actually comes from the composition of our atmosphere. So if we just look at the dry atmosphere, so this is the atmosphere without water vapor. About the vast majority of our atmosphere is diatomic nitrogen. It's N2. We don't really interact with it much. Plants do when they do nitrogen fixation, but we breathe it in. We don't notice it. We're more concerned when we breathe, breathing in the diatomic oxygen part, the O2 part. That's the part that helps our cells do aerobic respiration, allow us to make a lot of ATP and have a lot of energy for our cells. We need oxygen to do that. So 21% of our atmosphere is oxygen. And 1% of our atmosphere is argon. Argon's an inert gas, doesn't do chemical reactions. All of its orbitals are filled, so its final valence shell is filled, so it's not going to do any chemical reactions. It's what we call a noble gas. It's just straight argon. And so this is 99% of our atmosphere. Nitrogen, oxygen, and argon, okay, of our dry atmosphere. Now, the reason I didn't put in, well, before I get to that, now, I should point out that neither nitrogen, oxygen, or argon absorbs infrared photons, okay? They don't absorb visible lights, and they don't absorb infrared. So all the stuff that is being emitted by the sun or off of our planet, this is totally transparent to it. So this really has no effect on our one-layer atmosphere. Now, I said that this was the dry atmosphere. Why am I just talking about the dry atmosphere? It's because if you talk about water vapor in the atmosphere, it's a little bit more complicated because it's different in different regions. Okay, you've got hot tropical regions and cold polar regions. So in the hot tropical marine atmosphere, about 4% of the atmosphere is water vapor. But if you go to like the poles, where it's really cold, you have a lot less. Warmer air will hold more water vapor than colder air. You know, like if you go into, like say you open a freezer and you see all the like frozen kind of snow and ice in the freezer, it's because when you first opened it up, you had warm air rushing in, which had water vapor. Then you closed it, the air cooled down. So all of that water vapor condensed and formed ice in your freezer. Now the air inside that freezer has very little water vapor. It's all precipitated in the form of snow and ice. The warmer the air, the more water vapor. So when you get to the hot tropics, it can hold a lot more water vapor. And this is important because water vapor does absorb greenhouse gas, or does absorb infrared radiation. Okay, so it's actually the most abundant greenhouse gas, which is interesting. Okay, so let's go through what we have so far. Nitrogen, which is 78% of our atmosphere, it does not absorb in the infrared. Oxygen, which is 20% of our atmosphere, does not absorb in the infrared. Argon, 1%, does not absorb in the infrared. Water vapor, anywhere between 0.2 to 4%, that does absorb in the infrared. And now we've got like 99.95% of the atmosphere. You might think that the other part of the atmosphere, you know, the remainder, isn't really all that important because we're just talking about 0.05% of the atmosphere is whatever else is in there. But it turns out it's incredibly important for the fate of our climate. Okay. And we're going to have to probably switch from percentages because 0.05% is really hard to work from. So we're going to go to parts per million. And so it is helpful to know percent is just like the number out of 100. So if you have 78% of something, that means 78 out of every 100 molecules of the atmosphere is nitrogen. When we go to parts per million, it's that number for every million molecules. So for example, carbon dioxide is 410 parts per million. That just means if you had 1 million molecules of atmosphere, 410 of them would be these CO2 molecules. And carbon dioxide, it turns out, strongly absorbs infrared photons. It is the most important greenhouse gas when it comes to human change, human-caused climate change. So if we put this table into parts per million, you can see that we've got carbon dioxide, we've got methane. That's also an important greenhouse gas, but you can see it's a lot less in terms of its abundance. Nitrous oxide is also in our atmosphere, as is ozone. It's also a greenhouse gas. Most of the ozone is much higher, however, and that's really important for another reason, because ozone absorbs really high energy photons like ultraviolet photons, which protects us from ultraviolet light coming from the sun. That's why white people get tanned when they go outside. It's all those UV rays. And when we have a hole in the ozone, that happens a lot more. And then the other thing that's out there are halogens. So these are like chlorofluorocarbons or chlorocarbons, and those would be in the parts per million. But I don't want to overwhelm you with all this stuff. I really want you to focus on how these climate models, how this modeling of climate works. You know, whether it's a simple one-layer problem, or it's a two-layer problem, or 3 or 4, adding each additional layer of the atmosphere brings up the temperature. If the atmosphere absorbs in the infrared, right? If the visible light can pass through it, but the infrared can't, and the infrared is how the energy goes back out into space, and it gets trapped in that atmosphere and warms that atmosphere up until it's radiating enough so the outer layer of our atmosphere radiates as much energy out as the planet took in energy. And then the little ball, the Earth ball floating in space, will be giving out as much energy as it's taking in. And so its temperature will stabilize at this number over here. That's the number it'll stabilize. If something happens in our atmosphere and CO2 increases suddenly, and all of a sudden we're not emitting enough energy out, and we're taking more energy in, then we're going to have to heat up until that outer layer is emitting as much energy as the planet is taking in from the sun. So give me some questions here. This is a lot of data, right? Are we lost? Is it making sense? What's our story? Desire, let me hear from you first. You got some questions?
Not really questions, but yeah, it's getting a bit deeper than I thought, and we need to put in more work so that we can grasp the concepts better than we are doing, because you are posing quite some questions here and there, and I find it I'm getting it that we are finding it a bit difficult to just answer instantly. We have to think twice and process.
Sure. Well, this is all new to you, right? It's all new to you. But the purpose I'm getting you to, when I ask you those questions, just to get you thinking and seeing kind of where you're at. Now, when we talk again on Monday, we'll probably just work through a few of these problems. And this is actually as far as we're really going to get into the physics. When we end up with that N layer formula, and we understand that as we add layers, that we increase the temperature, because this is the basis of how climate models are made. It's these kind of calculations, energy in, having the equal energy out, and the fact that we have an atmosphere, there are chemicals in our atmosphere that can absorb in the infrared. And the more of those chemicals we have that can absorb in the infrared, the warmer our planet's going to get. And this is why it's going to get that way. And so this is as deep as we really need to get into the physics. We'll talk about, atmospheric composition. We'll talk about, how much of a difference layers of carbon dioxide make in the atmosphere. And then we'll start talking about, well, where does the carbon dioxide come from in the atmosphere? Because that's the thing that's changing the most. If you look at our climate over long periods of time, like even back to the paleo climate, like we were looking at before, the amount of nitrogen in the air has been the same. Amount of oxygen has changed a lot, but it's not a greenhouse gas. It shouldn't affect warming or cooling how much O2 we have. Same thing with the amount of nitrogen or argon. So what's changing? If energy coming into the planet is always going to equal energy out, why didn't we just stay as cold as we used to be in the ice age? It's adding these layers of, and when you look at the climate record, you'll see, and I think I showed that a little bit early, that one track with the climate record, if you look at the levels of CO2. As the levels of CO2 go up, it looks like the climate's going up. That doesn't mean it's causative, but now we're starting to see from this, if you add amounts of CO2, the temperature will have to rise. And so now the correlation, we now see evidence that there might be, a connection. It might be causal as opposed to, so we're not going to get too much further into the physics. This is about as complicated as we have to go, but it needs to be explained, one, because we need to understand where these climate models come from and what they're saying. Because if we're going to, by the end of this program, if we're going to be posing things that will help, say, fight climate change, we need to really know, how much of an effect and how you calculate. How does that affect the climate model? For example, biotechnology, there's a company in California, in the US, that has been doing genetic engineering with trees. They've modified the metabolism of these plants to grow almost twice as fast. Okay. And so the question, and so remember, when a tree grows, the actual physical, like the wood of the tree and the plant matter of the tree, that's all made from carbon dioxide. It doesn't come from the soil. That's why when you plant, seeds in a little pot and you water it every day and the plant grows out, you don't have to keep adding dirt, right? It's not like, oh, it used up all the dirt, I better put some more. That's not where even though the plant's getting huge, maybe even too big for the pot, the amount of dirt always stays the same. You got to add water. Well, where's all the mass of the plant coming from? It's fixing the carbon in the air and making it into sugars that make up the plant. And so, this company wants to make trees that grow twice as fast, so we might be able to fix a lot more carbon in the air. Well, how many of these trees would you need to plant in order to fix the climate problem? We'll see later on about tree planting that there isn't enough room on the planet to just plant enough regular trees that it would solve our climate problem. There's just not enough room. but maybe by making more efficient trees using genetic engineering and biotech. Can that be part of the problem? How will it affect our climate models? How many layers of carbon dioxide can it remove, et cetera? We'll be able to relate layers to the ppm of carbon dioxide, and then that will just be kind of the end of our physics portion, because then we'll understand exactly how much energy and temperature we're talking about for every so many ppm of carbon dioxide, what kind of a temperature change we're going to have on the planet. Now, there's also complicating factors like, well, we know that ice melts when it gets warmer, and ice is part of our albedo, right? That reflects light back out into space. And so to really understand climate change, we needed to understand the nature of the albedo, right? If that 0.3 now turns to a 0.2, well, now the energy coming in from the sun is a lot more. It's not 238, it becomes 338. Well, now all those fluxes change and things have to get a lot warmer if our albedo is a lot smaller. And our albedo is due to clouds, and it's due to ice and particulates in the air. And so those all factor in. But now you guys know the physics of climate change. When we go through this and work, do a couple problems where you feel, you're facile with it and you can do it, then you'll know all there really is to know about how the physics affect it. And then it's not like, do you believe in climate change or not? It's just math, right? So I appreciate you guys bearing with me on this. And I will slow down. I'll come to a stop. On Monday, we could just go through a bunch of problems and kind of work through it that way. So you all feel comfortable with it. But don't think that the rest of the course is going to be all this physics-based stuff. We got a lot of other fun things to talk about with climate change, but we first needed to know what the amounts of climate change were, hence the indicators. And then that didn't tell us why it was happening. Now we've got to figure out the why, so then we can see what, why these things are happening. And then we're going to spend a lot of time on the effects all over the world, what climate change is doing, how it's impacting communities, how, specific things that climate change is doing all over the place. Any questions? Okay, cool. Like I said, I've seen everybody's peer teachings. I'm uploading my video responses. I've already made them. Your grades are in Moodle, but you should be getting links to those later on in the day today, so you can see my responses and stuff. I think one person's went public, so you can go ahead and check that out. And I'll see you all on Monday.
Dr. Panasi.
Yes. Bye-bye.